All right, finally, we'll prove 3 implies 1. So first, the global assumptions, just stating them again. Let A be an algebra of sets on X, and let mu be an additive function. Then we're going to assume 3, so we're assuming that mu is continuous from below. And our goal is to prove 1, that's that mu is countably additive. So to prove mu is countably additive, I should consider any sequence of fancy sets in fancy A. I guess you could call them fancy sets if you want to. And let's assume they're pairwise disjoint. And what else? And also we need the union. Let's call that A. So I'm defining the A to be the union of these, and I need to assume that that's in there. That's not automatic because this is not necessarily a sigma algebra here. Then our goal is to prove that mu of this union is the infinite series that you get when you add up mu of all the ANs. Now, to apply my assumption of 3, I need to be in a situation where I have some family of sets building up to a set, right? These ANs, they're not like that. They're disjoint sets, right? So how do I put myself in that setting? Here's one way. So let Bn be, for each n, let Bn be the union of the ANs up to n. So instead of looking at the sequence A1, A2, A3, etc., look at A1, A1 union A2, A3 union A2, union A1, and so on. For all n. Then definitely the union of the Bn's is going to be the same as the union of the ANs. That's pretty easy to prove. So that's what I refer to as A. And now it's been designed so that B1 is contained in B2, is contained in B3, etc. Right? They're nested in this way because each one is the union of the previous one with an additional thing, right? So in other words, the Bn's build up to A. That was the point. Now, can I apply my assumption, which is that mu is continuous from below? What else do I need other than Bn builds up to A? I need A to be in there, but I'm assuming it is already, and I need the Bn's to be in there too. Is that true? So let me state it and then see if I can justify it. And each Bn is in there. So is that true that the Bn's are in there? Well, the Bn's are finite unions. They're defined to be finite unions of these A's, which are in fancy A, right? Fancy A is an algebra of sets, so it's closed under finite unions. So each one is in there. Let me make it a parenthetical comment, because this is an algebra of sets. So it's closed under finite unions. So now I'm in a setting where I can apply my assumption that mu is continuous from below. Since mu is, and I'm putting this, we could just define this term officially, but I don't want to, so I'm just going to put it in quotes every time, but you know what I mean. I mean that condition number 3 there. Since mu is continuous from below, mu of the Bn's, this sequence of real numbers, has to converge to whatever mu of A is. All right, that's good. What did I want, though? So this is some progress, but what do I want? I want mu of A to be written as a series. The series consisting of mu of the ANs, right? That's countable additivity. But remember that mu is additive. There's this global assumption here that mu is an additive function. So we at least already know how to handle finite unions of disjoint sets, which is exactly what these BNs are, finite unions of disjoint sets. So we have mu of Bn for each n. We have mu of Bn is mu of this finite union of disjoint, right? We were assuming these ANs are all pairwise disjoint sets, all in fancy A, and mu is additive. So this is the sum of these, right? In other words, I mean, typically we write with this notation. Maybe like this. It's a partial sum, right? It's a partial sum of the series that I'm interested in. So what am I saying here when I say this sequence converges to there? I'm saying the sequence of mu of Bn's, the sequence of partial sums here converges to mu of A. That's the same as saying this series converges to mu of A. So therefore, mu is an additive, is a countably additive function. All right, so now we've proven that countably additive can be expressed in these two other equivalent ways, which are sometimes easier to work with. Sometimes it's easier to work with a family of nested sets rather than a family of disjoint sets. And like I said, this is what we're looking at is what it takes for mu to be called a measure. So these are different ways of describing the condition of being a measure. So let's state that definition and then end the lecture. So I'll state that in the next video.